So, welcome to this session, everyone. Thank you so much for coming here. There are so many great sessions parallelly happening, and the fact that you considered this is worth your time means a lot to us. So, this talk is about how can you modernize and migrate databases on-prem to cloud by the way of Confluent and Kafka. Before we get there, a bit about myself. I am a solutions engineer at Confluent. What that means is I help customers with solution architecture to product advocacy to everything in between, solving their streaming data problems. And I have here Srini. I'll let him introduce.
Yeah, we'll scroll next. Yeah, I'm Srinivas. I'm a senior manager of data analytics, managing our PSS in data analytics and DevOps segments.
So this is the breakdown of what we're going to do today, right? We'll introduce to the problem. Why do we think even migrating modernization is needed in complex databases? And with every problem we have, there's always an opportunity to create something new, just like Confluent did. And that's when we'll discuss the why, the what, and who of the Confluent's partnership with AWS, our common goals, and our shared passion for creating not creating problems, so solving data streaming problems on AWS. So we'll spend some time on the proposed architecture, and if there's time left, we'll spend the time for Q&A. So the architecture is for a real-world use case for a real customer, where we try to mimic that situation in our demo format, where you will be migrating data from an on-prem Oracle database to RDS, specifically Aurora. And we'll discuss the ways and means of how you can leverage this lower operational cost that comes out of the box with Confluent Cloud and AWS Aurora. So let's get started. We need to first discuss why do you even have to modernize these databases, right? They're fine by themselves. They've been around for so many decades. They are legacy systems. The big giants love them. Why should we even modernize them? So we all know that this is a cliched phrase, but I'll say that anyway. The data is growing at this unprecedented amount of rate, and the volume is just, it's like crazy. We've seen the numbers at Keynote. They are mind-boggling. It's only going to grow more. It's evolving. And the companies right now are suddenly realizing the need to introduce this conceptualization, harnessing all this data in motion, that way that they'll enable their own data teams to make better operational decisions, which will help them act in response to their customers' needs anywhere, from everywhere and anywhere. In order to do that, they have been doing this on-premises, but these legacy systems like SQL servers, Oracle, and all your MySQL servers, they are rigid, and they're actually slow. Because of this, they're also expensive. You have licensing costs, you have other vendor lock-in requirements that need you to pay a lot of money. Because of this reason, there is a limitation introduced to the pace at which you can innovate or drive any sort of experimentation on these platforms. So because of that reason, and you also cannot scale these databases when the workload is evolving. It's a fact. So we're all in this SaaS world, right? I have this quotation I really like a lot. It goes like this: the only thing that can be worse than developing your own software that you can buy from someone is running the system that can be run by someone else. That is the unfortunate truth that we don't want to run. We want to focus on building these applications. But unfortunate truth is that they have to operationalize, also build these apps. Which is hard, I can only imagine, and traditional systems are not built to do that. By migrating to a cloud-hosted database like Aurora or RDS or whatnot, right, you're taking away all this burden suddenly, and you are lowering the TCO, and by improving your agility, flexibility, everything that you see on the slide, because you're decoupling the storage and compute. You probably heard this over and over again, but that's really the fact. So. And all these cloud providers, especially AWS, they've built this amazing model of pay only for what you use. And this is a consumption-driven model. All the SaaS companies like us are practicing. And it also, more importantly, you don't want to hire tens of DevOps engineers who will want to keep the lights on and their weekends are all gone. And we don't want that. We want to save their weekend. That's why Confluent is here to but before I get to Confluent, there are these larger companies that utilize data in motion paradigm. They still find migrating data very hard because from legacy systems to wherever they're moving, it's still a hassle and a task of itself. Now, in order to do that, this migration, right, it involves multiple teams. And traditionally, all the processes are batch-based, meaning which you only have historical data, not really real time. You have some processes in place right now, but they're not really efficient at scale. And then, yeah, so I did not cover everything on this slide. So, yeah, so that way, you're basically, if you want to replicate the data from on-prem database to a cloud-based one, it is really time and resource intense, compute intense to move data to a multi-regional, multi-zonal cloud or cloud providers. Because that is so hard, you really want something that fits into the model, like cloud natively. That's not provided by these legacy databases. And one other issue we have, and did I go fast? Yeah, so one other problem you have is that you really, yeah, you don't have out-of-the-box connectors or an ability to transform data in these databases by themselves. You'll have to employ some form of a layer on top of these databases. That is, again, another expense they have to invest in. And also, not to mention the way the data is siloed by these, because like there's this latency issue, and also because of the silos of data you're bringing in data from, there's like inevitably there is like latency and the data is stale. It is not suitable for real-time, time-sensitive use cases. So you need a solution. And that's where I'm going to go at Confluent. We are here to accelerate and simplify all this migration process, make it seamless. We also help you enhance in real time by the way of a tool called as KSQLDB, which is inbuilt for you. Once you have the data in Kafka, you don't have to employ another third-party tool like an ETL or a transformation tool. KSQLDB comes with a, I'm going to go deeper into this in the later slides, but that's the gist of it. You can transform on the fly. You can connect data from disparate sources with just everything inbuilt by Kafka for you. So what better solution than that, right? And you can, by the way of all this, you're reducing the TCO, you're all the good things, like you can scale, fault tolerant, and globally available. You want a solution like that. We're going to discuss the demo. You'll see the demo where all of this will come into action, and it will showcase the abilities that I just spoke. Next. So why do we want, how can Confluent on AWS can help you overcome these challenges that I just discussed? There is this new, before I get to that, I need to talk about a new paradigm that Confluent has pioneered. It's called as data in motion. Data in motion phrase has been around for several years, but Confluent actually redefined the way data infrastructure is viewed, meaning which you have built this infrastructure, you have this real-time data flowing in. In order to marry these both, you have to have a solution that is inbuilt, not necessarily, not something that you bring from outside. So Confluent is really pioneering in this space, I would say, and they actually, they've invested several hours of engineering time in building this entire platform with the expectation that everything was going to become real-time at some point. So if you see all companies, not just our customers, are completely rethinking their strategy from data at rest to data in motion. We have a customer, Citibank, who said this. I'm going to read straight down. We need to shift our thinking from everything at rest to everything in motion. Quotes. This is from Citibank. If this is coming from a bank, which needs highly secured environment, they only prefer on-premises. This is from banks. So they are preferring to move to cloud, and they are trusting someone like Confluent, which is a SaaS vendor. So you can only imagine giants like social media platforms and all the big companies, or the ride-sharing apps, who are moving towards this data in motion, quote-unquote, paradigm. You need a solution. And that is powered by Kafka. Kafka is nothing new. It's an open source tool that's been around for more than a decade now. But we need to talk about operationalizing Kafka. If you know Kafka, if you've used Kafka, it is a distributed system written in Java for developers initially. But operationalizing something like that, it is a task in itself. Deployment might seem easy, the OSS Kafka, the open source Kafka, but as you evolve your workloads, it is hard to experiment. And it's even harder when you have more workloads that are just really unstructured or there's no pattern for them. You just have to figure things out on the go. That gets even more harder. And these companies who are embracing this Kafka as their central nervous system, they inevitably find themselves running into these challenges, like they have operational burden, which is like you can't. This is a complex system. We're talking about hundreds of nodes, producers, consumers, and a lot of replication happening under the hoods. So that burden is still there. And nowadays, everything needs to be secure. Governance is a key element for all enterprises. So that is there for you. And connectivity. Like we're talking about real-time analytics performed from multiple sources and sinks. So in order to do that, open source Kafka can only do so much. They have some connectors, but not really a robust end-to-end comprehensive solution. So that's where we also need a highly available solution. So Confluent has really thought about this, and in this multi-phased project, we've analyzed several customers, and back in 2014, they started to realize that this is much more bigger than open source Kafka. We need to productize this. So that's when they went ahead and created Confluent, and then eventually the SaaS offering from Confluent. So this slide actually talks about how hard the self-managed solutions right now who are helping with migration. I don't want to take the names, but there are a few solutions that are doing a decent job, but we're talking about time to migration weeks, if not months. And there is often a dependency on devices like Snowball. You have constraints like bandwidth. Several of these devices to be transported everywhere. Your data has to be moved. And also the dependency between application teams is growing more and more as the companies like Meta, Google's and all, they're introducing new projects that we don't know if we even need them, but they are introducing all these new features and throwing at our faces. So you have these several teams depending on each other. So migrating this data, those legacy databases, which will stay and will stay forever, I guess if not forever, we're talking about 2-3 decades from now, they will be around. So we need to figure out a way which is not just fire and forget, but that evolves continuously. That is something you're working on a regular basis, rethinking and reinventing the way you act on the data. So that's what Confluent has worked on, designing this cloud native. Now comes the new requirement for all these enterprises that you have to become a cloud native solution. This is what Kubernetes has introduced. This is an awesome, like Kubernetes is awesome, but it made things much more, how do I say this? But people want more, but in order to get there, you need a solution that's out of the box. They don't want to invest time in building all these things, right? So Confluent came up with this. We have re-engineered Kafka ground up in order to make it cloud native, in order to harness the power of cloud. So meaning which, what does it mean? There are 3 main pillars that Confluent really focus their efforts on. First thing is all the Confluent cloud clusters or Confluent platform clusters, the Kafka clusters, they are all provisioned at the click of a button, meaning which you just decide the throughput, the throughput, the latency requirements, and you decide. It's just as easy as you go provision an EC2 machine. It's just that easy. Underlying everything is run by Kubernetes, powered by Kubernetes, so you have this elasticity out of the box. You can scale up and down as per your workloads. It is also global, meaning which we are across several regions on all cloud providers. There's infinite storage, meaning which so you can store data. If you know what how Kafka works, there are brokers, there are consumers and producers. You can choose to store the data on these brokers, which is basically you're talking about hard disks. And that's not an efficient way to store data, especially Kafka, it should not be used as a database, so it's a streaming tool. So what we have done is we have introduced something called as tiered storage, which is basically infinite storage. You can offload all the broker's burden onto an object storage like S3. That way, your data stays warm or cold, and you can retrieve them as you need. This is something that differentiates Confluent significantly from open source Kafka, other vendors, because that's not there yet with them. And we are supporting it from ground, right, day one, where we have infinite storage. That's what powers the whole Confluent cloud. Right, so that's a little bit about how we have evolved from open source Kafka to our own platform offering. When it comes to Confluent, right, we want to span wherever your data is, meaning if you want to offload everything to us, we can do that with a fully managed offering. But if you have expertise in-house and if you want to self-manage Kafka clusters in public clouds or on-prem, you can still do that with the help of our support, and that's platform for you. Really, it is so simple that irrespective of your deployment model, you can still choose to connect data between this cloud and on-premises Confluent platform. We have tools for that comes out of the box. You might have heard of Mirror Maker, Replicator. Cluster linking is another tool that is from Confluent, which is like surpasses all the good qualities that Replicator has for you, which is open source. Mirror Maker is open source. So cluster linking brings best of both worlds, and we also built so many features on top of it. You can move data from Confluent Cloud, which is on your cloud provider, to on-prem or vice versa. It's that easy. Now I'd like Srini to take over, and he'll talk about a bit about the evolution of databases on Amazon and Aurora.
Thanks, Geeta. So basically, we'll go over our AWS ecosystem. I'll go over what is modern data strategy is. So modern data strategy, we define it as first migrating to the cloud, and then coming up with a platform where you can scale as per your need at optimum cost, as well as meeting your operational needs. So what basically from our early learnings from operating infrastructure at Amazon.com, what we learned there is although the traditional relational databases, they have their own capabilities, but what we realized that is in many instances they fell short. So because of that, we innovated on behalf of our customers to come up with relational databases, which Geeta mentioned, Amazon Aurora and RDS. So when we were going through when we were talking to our customers, we realized that some of the workloads may not be tabular data models. So we came up with Amazon DynamoDB, which is a key value pair. It can scale to sub-millisecond performance at any scale, basically. And then what we figured out that there are some cases where the intersection of data types, access patterns, and user preferences needs a different kind of non-relational databases so that our customers can use the right database for right workload. So as you see, we have many databases that came out of our discussions with our customers, which are designed for the cloud. One of them is Elastic Cache for your in-memory workloads. And then we have DocumentDB. If you have JSON type of documents, you can use DocumentDB. So we have Amazon Neptune, which is our graph database. TimeStream we launched for streaming data. So we have a wide variety of databases. So our customers now, they can actually use the database that basically meets their workload for that particular use case. So what is Amazon Aurora? Amazon Aurora is an enterprise database from AWS. It not only provides speed and availability of your high-end commercial database, but it also provides the simplicity and cost effectiveness of open source database. It is MySQL and PostgreSQL compatible. That means your existing applications and tools can work seamlessly with Amazon Aurora, as well as we have our own developer tools that help you to build serverless or machine learning powered applications using Amazon Aurora. And it comes with 1/10 of the cost compared to our enterprise relational databases. This is one of the fastest growing service in AWS. As you see, these are some of the customers who are using Amazon Aurora. Out of 1,955 of our customers are using Amazon Aurora. So I don't go over all the list. So we have several of them. So Amazon Aurora it provides the performance scalability of enterprise data warehouses and the availability durability, which I will go over in the next slide, the way how Amazon Aurora underneath works, the architecture of Amazon Aurora. Is highly secure. The data at rest and data in motion are secured. It's fully managed by AWS. So I'll go over what fully managed by AWS means in the coming slide. So this is how the Aurora architecture looks like. So this is a single master Aurora architecture. As you see, the storage layer, which is a cloud storage volume, which is spanned across 3 availability zones. And you have a master database and read replicas. So a single master Aurora looks like this. Master takes the read writes, and it writes to the cloud storage volume. The cloud storage volume, the data is in 10 gig chunks, is replicated 6 ways across 3 availability zones. So what that means is it can withstand failures of 2 data copies and can still take writes, and it can withstand failure of 3, can still take reads. And the read replicas, it supports up to 15 read replicas. This is for read workloads, and the writes go through the master. In case of any failure of the primary, and one of the read replicas would be promoted to the primary. So that which read replica can be promoted, that's the priority, you can set it up. And another feature of Aurora, a service we have is the serverless Aurora. As you see, the serverless Aurora basically provides you, you don't need to manage any DB instances. You just have to spin off you just have to connect to serverless Aurora. It automatically scales up, down. It provisions it adds the storage as needed by your application. So your application in 10 gig increments, and I think the limit it can go up to is 128 terabytes. So you don't need to worry about provisioning the capacity or anything. Everything is auto-provisioned. Based on your application needs, the data goes up or down. So you pay only for the amount of data your application needs. Because of that, compared to the provisioned capacity, if you use serverless Aurora, it saves you almost 90% of the cost. So these are some of the core features of Amazon Aurora. I'll go through some of them. One is, I just talked about the serverless component, global database. If your application has a global application, needs to be available globally, so what you can do is you can use Aurora with multiple regions. So the Aurora database spans different regions, so that if there is a failure of the primary region for any case, in an instance, one of these other Aurora databases in a different region can be promoted, right? This happens in a second. If you would like to basically, underneath, what happens is we use this, in the previous slide, whatever I've gone through, the storage replication across regions. So the storage replication happens in less than a second between regions, but if you want to promote a region, Aurora in a different region, that takes, I think, within a minute. So that is one of the feature. And the other one is it automatically backs up. It does the recovery also. 6 copies across 3 multiple availability zones is already automatically done by Aurora. That means every data set in 10 gig increments is copied 6 ways. So even if some of the, if 3 copies fail, it can still take reads. If 2 copies fail, it can still take writes. And the next feature is, it's MySQL Postgres compatible. That means all the existing MySQL tools that you use for export, import, PZ dump kind of tools that you use in Postgres, they all work seamlessly with Aurora. It is fault tolerant. RDS proxy is something you can put in front of Aurora. Basically what happens is all the connections would be available at the, it keeps track of all the connections and it caches it. So in case there is a failure of database, the failure time will be reduced because the connections are there at RDS proxy and it can connect to Aurora whenever a new database instance is available. And it has several integrations for if you would like to see how the users are accessing. For example, for banks and all, you have all the compliance, POC, SOC compliance and PCI, HIPAA compliant. If you would like to, then you can make use of its integration with AWS Cloud Trail, where you can keep track of all the users who are accessing the database as well as the API calls they made. It has integrations with CloudWatch. That means out of box, 20 metrics, cache hit ratios, the performance of the database, everything you can visualize in the AWS management console. But if you would like to look at the operating system where the database is running, the metrics of the operating system, it is something called enhanced monitoring. Once you make use of enhanced monitoring, you can see the operating system metrics also. And there is another tool we have, which is RDS Performance Insights. You can make use of that tool to get further insights into what Aurora is doing. And it has integration with DevOps Guru. DevOps Guru is a machine learning powered metrics data that you can use to get more data points about how a particular system is working at any given time. It uses machine learning integration with that. And it has, out of box, it has integration with our Amazon SageMaker. So what that means is, if you use a machine learning query inline, you can directly get inferences from the database. So you don't need to go and make a separate call to SageMaker. Aurora has integration with SageMaker. So in the SQL query, it makes a call to SageMaker endpoint and gets the inference. So if you like to get near real-time fraud detection, that kind of use case, you can make use of this feature and do that. So these are some of the features Amazon Aurora has. I think with that, I'll give it to Geeta, who can go over what exactly the solution, how Confluent solved migrating Oracle database into Aurora.
Yeah, we've seen how awesome Aurora is and how it integrates with other AWS services, right? And why would anybody not want to make use of that facility? So this use case is about moving data from your Oracle on-prem to Aurora via Kafka. So there are several ways, but this solution focuses on how you do it with the help of Kafka's inbuilt tools. So this is a bird's eye view of architecture of Confluent Cloud on AWS. So if you look at it, right, if you're on open source Kafka already, or if you have a self-managed offering of Confluent platform, or if you prefer to get offload all the burden to us and have a Confluent Cloud version or subscription with us, it is all seamless with Confluent on AWS. So there are tools like cluster linking, which will help you act as a bridge between your on-premises data, on cloud data. And as you can see on the right, there are several disparate systems that on AWS that Confluent can help link to. I'll tell you how we do that. So the gist of this slide is to tell you that we help that data migration or movement, if you will, in a very seamless fashion with the help of tools like cluster linking and replicator. And it goes vice versa also. And because this use case requires a plan, we have a 3-phased plan for this. First thing is we have to identify the workloads that can be migrated. If you're aware of how databases work or data warehousing works, not all workloads can be moved onto cloud. They're not suitable for their existence on cloud. So that's where you have to choose your workloads that can be migrated. And then you can leverage our fully managed connectors that are made available for you out of the box. If you choose to self-manage your connectors, we will still help you with that. After you identify the workloads, it is now time to optimize that data with the help of KSQLDB, which will help you perform these real-time data aggregations and transformations on the fly. You can even perform windowing with KSQLDB. I'll get into KSQLDB in a bit, but it is just, it's so awesome because it comes with a familiarity of SQL-like interface. You can use that to write your queries, fire them, and forget. And they'll be running on the background for you with all the data that's flowing in, as opposed to the SQL interfaces that you usually are used to, which will run and stop at some point. But KSQLDB queries are on the fly. They always keep running. We call them persistent queries. With all the new data that's being added to the old data, it keeps changing the windows and giving you the new outcomes on the fly. That's the beauty of KSQLDB. And it works very well with the other parts of Kafka as well, like connectors, if you have other cluster linking, or if you want some other clients of Kafka to talk to KSQLDB, that is all seamless. Once we identify, optimize, and then it will then be time to modernize that data, move it to the final destination, which can be anything. In this case, it is Aurora. So we'll be using another fully managed cloud connector of ours to do that migration. And as the data is evolving, the connector will keep syncing the data between Oracle and Aurora. So let's start with our connectors, right? Which will help you liberate your data from wherever it is on-prem to whichever disparate destination you want to move to. So if you're aware of Apache Kafka, it's an API on top of Kafka that allows you to source events from sources into Kafka with the help of an API. It's an open source tool that's been around for decades, but what Confluen did is that it expanded on top of that existing API, and we've built so many more connectors than what open source had to offer. There were around 80 earlier, and now we've built more than 130 plus, adding to what they were already there. So many of these early customers of Kafka, they used to contribute code to connect, and they used to build their own connectors because there was nothing available for them to connect data between, let's say, Cassandra and MongoDB. So now, at this point, we have introduced all these connectors already, so we're saving you the effort and time that goes into building them, which is usually from 6 weeks to 6 months. We're saving all that time. We're also saving you this operational risk that you might run into when you deploy these open source connectors that are usually buggy, and in production you cannot afford to deploy those connectors. So Confluen is saving your day that way. And you can, if you choose to keep data on S3 or any of those connectors that you see on the right, if there is nothing that's available for you, Confluen will build that for you via a feature request that you can open. And there are also partners that support our connectors. There are 30 plus of them. And we already have 100 plus connectors that are supported by Confluen. We have more than 40 fully managed connectors that are very popular. Now, this is the pipeline we're talking with. I've been iterating on. If you look at on the left side, there are these legacy systems you can pick from. You deploy a source connector, which is basically a Java program, a process that runs in conjunction with Kafka, and that will push all the data in batches or even in micro batches, or if you have a preferable interval at which you want data to be transported, source connectors can do that. There's a facility where you can configure this. Once that data lands into Confluen Cloud or Confluen Platform, you can use KSQLDB to perform all the transformations inside when the data is within the Kafka ecosystem. And then you will eventually use the sync connector, which is again another form of connector but functions differently. It will push data to your cloud-based systems, which are basically what you're seeing on the right. In this case, we are moving data to Aurora, RDS, Aurora. It can be anything, but it is all seamless. It's just, you'll see in the demo how easy it is to configure a connector and fire and forget that connector. The beauty about Confluent Cloud is that if you run into an error, it is self-healing. So you don't have to go intervene and fix a configuration. The team at Confluent will do that for you. So you're talking about hundreds of hours of Confluent Kafka expertise. We hire more than, I don't want to say this, but there are, I don't know if I want to be very clear when I say that, but we employ almost like 70% of committers of Kafka. So we're talking about, we do only Kafka, so you get that expertise out of from us. And I spoke about KSQL DB, but I'd like to, before I get there, so there are these sync connectors which are similar to source connectors. They are native to Confluent Cloud. They function slightly differently than source connectors, but the goal is to move data to the destination. Before we send the data to sync connectors, right, if you want to perform these simple aggregations, you can use KSQL DB, as I mentioned earlier. But you can also depend on something called as Kafka Streams, if you're aware of it. It's another Apache Kafka API that allows you to build Java applications or Scala applications, and it's also open source. You can go check out. It's primarily dedicated for real-time data streaming use cases. But we have that facility. In this slide, as you see, there are 3 columns. The first describes about, you write this really 30-line code where you're configuring a Kafka client which will produce data to Kafka. And that's basically how every Kafka client works. You write code and you do it. Instead, you can also choose to use Kafka Streams, which can to produce data to Kafka. And as you can see, the number of lines of code has come down to like 6 lines if you use Kafka Streams. And in the third column, in order to make this stream processing much more accessible and also approachable, what Confluent did is that they've built a layer on top of Kafka Streams, which is called as KSQL DB, which I've been drumming about. So KSQL DB is this GUI, there's also an API for KSQL DB, but primarily the GUI, which you can use to write these SQL-like queries, which, as you can see, the code that you wrote for Kafka Streams and Kafka clients, now in KSQL DB, it's just one line SQL-like query that will help you achieve the same result as you would with this other code. If there are developers who are not comfortable with Java or Scala, and they have the familiarity with SQL, this is a right product for them, and they can right away fire those queries, forget them, and it will do its job. And then, as we spoke about KSQL DB, let's dive deeper into this KSQL DB, right? So it's a purpose-built database just for Kafka workloads, and it's underneath, it is supported by something called as RocksDB, if you're aware of that. It's a database that stores state. If you know, Kafka is a stateful application, meaning which the state has to be retained, and every time a new query is fired, KSQL DB makes sure that these persistent states are saved in RocksDB, and in the event of any disaster, and RocksDB is also replicated. So you always have several copies of it in order to retrieve the data once, if you have, by any reason, one of those RocksDB instances goes down. And KSQL DB supports aggregations, joins, and windowing, and all those good things that SQL has to offer. And you have the ability to fire multiple queries, persistent queries. And all of this is, of course, the computational and all the storage resources that are going to go to KSQL DB are separate from the Kafka clusters. So KSQL DB feeds off of Kafka, but it's an entity of its own. So there's no resource contention. You can be rest assured that there is no competition between Kafka brokers and KSQL DB. And KSQL DB is also highly available because RocksDB is underlying, and it's also fault tolerant. So, I want to reiterate this, that Kafka by design is the background, backbone for KSQL DB. Earlier, KSQL DB was using Kafka as the storage layer, and then they moved on from just as storage layer to becoming the go-to aggregation tool. And then whenever you make an update to Kafka, it automatically updates KSQL DB also. That's the beauty of this creating, because you don't want to maintain 2 different systems, right? So when Kafka gets updated, KSQL DB also automatically gets updated. And that's why several customers like KSQL DB, and they have started using it because it's also resilient and it's easy to deploy. It's nothing you're deploying as a third-party tool. One other improvement, what they did recently is that they're going to announce soon many new additions to KSQLDB, but it's really a fully managed offering that's out of the box. It comes, you can scale and size KSQLDB for your needs, the throughput, like whatever Kafka data you're streaming through Kafka, if you want to stream them to KSQLDB, you can also size them in the, we have a unit of abstraction called streaming unit, CSU, and that will tell you how many CSUs you would need in order to support that much throughput. So now that we have gone through, this is just a repetition of the slide that we saw already. So that's KSQLDB, Kafka streams, and how connectors can be used to connect data from disparate sources to Kafka. And if you look at this diagram, right, this is metaphorically, you can think of Confluent as a central nervous system, like your human body, where brain and your spinal cord is connecting your peripheral body parts. Confluent is going to act as that central nervous system to connect all these cloud systems that are everywhere, and that is flowing data from all your SaaS layers or data stores that are on cloud or on-prem. It is acting as that central nervous system. I am reiterating on that. So it is also eliminating one thing. If you read about Kafka's history, what it did is that it removed or eliminated the messy point-to-point connections that were there, that were around for several decades. So by removing that point-to-point connections, we were able to modernize these legacy architectures, and that were slow, expensive, brittle. And now you have this fancy Confluent Cloud, which is light, which is really fast, secure, and there's this one data plane that you could use right away. So yeah, you will see the demo and how easy it is to deploy these connectors or move data. Basically, we have all these fully managed connectors that are there. If you want them to be secured, we also have mechanisms you can deploy in the GUI, also via API. If you have a private link or transit gateway or whatever is your choice of private networking, we support most of them. And if you want to go for your lower environments like public endpoints, we also have that facility to only leverage public endpoints for your less critical workloads. And then after that, you don't have to configure much. This is very precise. We made sure that you don't have to go through these several lines of YAML codes. Everything is through GUI. If you also go the API route, even that is much more simpler than open source Kafka. And yeah, as I mentioned, if you want to whitelist a few IPs that you want to connect Kafka clients from onto cloud and all other various combinations of these networking options, right? You can do that with the Confluent Cloud currently. So before we get into the demo, I'd like to spend some time discussing about what you're actually going to see. So the goal is to modernize the streams of data from Oracle into Aurora and also from RabbitMQ. So what we're going to do is we'll extract the data from Oracle DB using Oracle CDC connector, and we'll also stream data, transactional data. This is a fictitious use case. So we're streaming transactional data from RabbitMQ also to Confluent Cloud. And then once both the source data arrives, we are going to perform some transformations and aggregations and windowing using KSQLDB. And we're going to create some fraud detection models. The results are going to help the downstream systems to predict a fraud. That's the whole goal. So after we merge these data sources, we are going to do a fraud detection using KSQLDB. And then eventually, we will use a fully managed Postgres sync connector to push the data to Aurora. So the RabbitMQ will be sourcing the data from RabbitMQ using a fully managed RabbitMQ source connector. So this is something we already discussed. It applies the same to this use case as well. We're going to identify a workload, which is, in this case, transactional data on Oracle. We have identified the connector that we want to use, which is Oracle CDC connector. We are now also going to optimize it. Basically, we're doing fraud detection. So we're going to run a bunch of queries in KSQLDB, which will optimize and consolidate that for you. And then finally, we're going to use Postgres sync connector to push data to Aurora. So I'm not sure why this slide is here, but yeah, it's basically talking about how you're simplifying this whole migration process with the help of connectors. Now, once I hit the next button, the demo will actually start playing. My colleague Joseph actually generously lended his voice for this demo. I did not do it, but I hope you like this.
Today, let's look at a pretend fintech company. We'll call them Acela Loans. Let's look at how they go about their database modernization journey by migrating data from Oracle database in RabbitMQ to an Amazon Aurora Postgres cluster in AWS. Let's say Acela Loans recently acquired a small bank that uses Oracle DB to store sensitive customer information and RabbitMQ as a message broker for credit card transaction events. Acela Loans wants to perform real-time credit card fraud detection analysis to protect their newly acquired customers and push the suspicious activity flags to Aurora, their modern cloud-native database that powers their mobile app's in-app notifications. However, they face a couple of challenges. First, the customer and transactions data they need live in two separate systems, Oracle and RabbitMQ, and they'll need to access and merge the data in order to get a unified view of their customers' credit card activities. Second, they'll need stream processing in order to build a real-time application for fraud detection. Using Confluent, we can build and scale real-time hybrid and multi-cloud data pipelines that move data from any source environment to the cloud database of your choice. Let's go through an overview of our implementation steps. First, we'll extract customer data from Oracle DB to Confluent Cloud using the fully managed Oracle CDC Source Premium connector. In this demo, we're using an Oracle database that is accessible from the outside. However, you could connect to any Oracle database either on-premise or in the cloud. Next, we'll mask sensitive customer PII fields as the data streams into the Kafka topic using SMTs on the fully managed Oracle CDC Source Premium connector. Then we'll extract transactions data from our second data source, RabbitMQ, with the fully managed RabbitMQ source connector to Confluent Cloud. Once all of our data is in Confluent Cloud, we'll merge the two data sources with KSQLDB, generating a unified view of the customer and their credit card activity. To help build out our real-time fraud detection use case, we'll leverage KSQLDB, aggregates, and windowing to create a customer list with potentially stolen credit cards. Finally, we'll load the results into Aurora Postgres using the fully managed Postgres sync connector, where the team can do further analysis. We're going to do all of that with some sample customer and credit card transactions. At the end of the session, we'll have run through everything you'll need to be prepared for your database modernization journey. And with that, let's take a look at this step by step. Let's start by taking a look at the customer data we have in Oracle DB. In the customer table, we'll have customer ID, customer first and last name, date of birth, average credit spend, and some other customer information. We're going to be using the customer ID field later to match our customer data to their credit card transactions data. Navigate to the connectors page under the data integration menu and search for Oracle CDC Source Premium Connector. This fully managed connector allows you to reliably and cost-effectively implement continuous real-time syncs by offloading data from Oracle DB to Kafka without any operational overhead. That's awesome. To configure the connector, we'll supply all the necessary information needed to access our Oracle DB. Near the bottom of the connector configurations page, you'll find the single message transforms related field, which we'll use to mask sensitive customer data. We'll enter a name for the SMT, DOB_mask. Then click Add Transforms to reveal additional fields. Select the transformation type as mask field $value, then select the field DOB on which the masking will be applied. The DOB field will be masked with the value provided in the replacement field, which we'll replace with XXXX-XX-XX. You can use any string value as a replacement here. Let's launch the connector and check to make sure it's up and running. Now, let's check the contents of this oracle.dbusers.customers topic to validate the records coming from Oracle. Here we can see that our SMT is working as expected with the customer's date of birth redacted and replaced with the string pattern of our choice. With our pre-built and fully managed Oracle CDC Premium Connector, you've now performed a highly complex integration with just a few clicks that would have otherwise taken on an average of 12 to 24 engineering months to replicate in-house, and even more time and resources to manage. Now, we'll switch gears and examine our second data source, which is credit card transaction data in RabbitMQ. Let's take a look at the transactions table. It contains fields like user ID, transaction timestamp, transaction ID, charged amount, and other relevant information. We'll need to get this data into Confluent Cloud as well, which we'll do using the fully managed RabbitMQ source connector. Let's create another Kafka topic called RabbitMQ_transactions for the transactions data. We'll search for and start configuring this connector. Similar to the fully managed Oracle CDC connector we used earlier, this fully managed RabbitMQ source connector also abstracts away all of the operational and management burdens associated with self-managing connectors. Let's tell the connector all about our RabbitMQ queue and connection details. Now that our connector is up and running, let's quickly step into the transactions topic and check out the events that are in there. Since the connector is running, it will automatically bring the updated data from Oracle database to Confluent Cloud after the initial setup. For example, if one of our customers recently increased their spending, we want to update average credit spend to make sure we aren't flagging transactions based on previous data. Let's go ahead and update Rika Blaisdell's average credit spend by 5,000. Now let's verify the new amount is added to Oracle DB users.customers topic. Voila, there you have it. Once all of our data is in Confluent Cloud, it's time to merge them and build our fraud detection logic using KSQLDB, which enables real-time stream processing with SQL-like commands. Let's start by creating a new KSQLDB application and writing some queries. First, we'll create a stream of customer data from the Oracle topic and a stream of transactions data from the RabbitMQ topic. Then we'll create a table using the customer data stream and the common field customer ID to join with the transactions data stream. Next, we'll begin to write the logic for detecting fraudulent transactions. We'll do this by aggregating the streams of transactions for each customer ID using a 2-hour tumbling window, and filter for customers whose spend in a 2-hour period is higher than their average spend. Let's create a new table called possible stolen card, sum their spend over the defined window, and compare that to their average spend. Now that we have our customer list with possible fraudulent transactions, let's load this into Amazon Aurora for documentation and further analysis. Before we jump into creating a connector, make sure your cluster has public access enabled and you allow access from any address or list of address ranges provided in the Confluent Cloud Postgres Sync configuration. Now we're ready to create the connector. We'll search for the Postgres Sync connector in Confluent Cloud, and similar to the source connectors, it's a quick and simple process to launch a fully managed sync connector to send data to your target system. Let's tell the connector all about our Aurora database, filling out the connection details, hostname, port, username, password, database name, your key format, your preferred insert mode, set auto create to true, your primary key mode, Kafka key record format, set your number of tasks, and launch the connector. With that connector fully provisioned, let's go over to an EC2 instance running the pSQL CLI and see what has happened. If we select from that table, we can see that all the data is here. We won't go through all the details, but it's sufficient to say that we've taken our data from our legacy database, joined it with other valuable data, and processed it with KSQLDB for real-time fraud detection, and logged the results in a modern cloud database, Amazon Aurora. Okay. Now you have a roadmap for how to modernize your database by bridging your legacy database in any environment to a modern cloud database with Confluent. Good news is that you don't have to use the same data sources and syncs we used in this demo because we have 120 plus pre-built source and sync connectors to meet you wherever your data and applications reside and help you get to production quickly and reliably. You can also check out additional stream processing use cases like the one we did for real-time fraud detection on the new stream processing use cases recipes page. You'll find step-by-step walkthroughs of examples from broad stream processing categories like anomaly and pattern detection, customer 360, predictive analytics, and more, along with SQL code you launch in Confluent Cloud with the click of a button. Thanks for watching this demo. We hope you found it helpful in thinking through how you can leverage real-time data streaming with Confluent to help accelerate your database modernization journey. If you'd like to learn more about how to build with Confluent and Kafka, be sure to check out our Confluent developer site where you can access tons of free courses on Kafka, Connect, KSQLDB, and more. And when you're ready to get started for free with Confluent Cloud, no credit card needed. Happy streaming.
That was Joseph. So I want to summarize. So Confluent is much more than Kafka, and we have invested so much of time in building in our own intellectual property on top of many things you'll see in open source Kafka. So it's like you have this complete platform which can be deployed anywhere and everywhere. And especially on AWS, it's a fully managed offering which comes as a zero operation service. I oblige you to go try that out. Confluent Cloud is free, as Joseph mentioned. You can go onto our website and you'll get a $400 credit for free. And check that out and let us know. That's it. I am done. So if you have any questions, let me know. Thank you so much for being very patient.